Good morning, students. Welcome to Complex Analysis Live Lectures. In this class, we'll discuss about elementary functions and their properties. Okay. So the idea is, for example, in real calculus, we already know functions like e power x, logarithmic function log x, okay, sin x, and trigonometric. This is sin hx, hyperbolic, or inverse, sin inverse x. All this, right? So we now, when you take z, which is a complex number, x plus iy, then can we talk about e power z, then log z, okay, sin z, sin hz. These are just example I'm talking. Okay, sin hz, sin inverse z, and so on. Okay, how we can define this? So we can define in such a way that when when our z is a real number, that means x plus I times 0, then whatever formulas we are defining, then these formulas whatever we define, they should agree with this real. Okay, fine. So let's see how we will have one by one. So the first one is exponential. So exponential function, right? Exponential function. So you take z. Z is any complex number. Z is any complex. Then we can write z in this coordinate form. Z is equal to x plus I. Okay. So naturally, how we can write e power z as e power x plus I times e power y, which we know this is same as e power x into e power y iy. Okay. So therefore, this you can write this as e power x into, by Euler's formula, e power iy is cos y plus I times sin y. Okay. So therefore, we will define e power z as e power x times cos y plus I times sin. Okay. Exponential function of any complex number z is defined in this, right? Oh. Now you can check that clearly when y is 0, then this is 1. You will get e power z is same as e power x. So one can observe some of the properties is that first one is e power z is same as e power x when y is equal to 0. Okay. Then we can easily see the e power, say suppose if I take z1 plus z2, this is same as e power z1 times e power z2. One can easily verify. So I ask you to everyone verify this. Why e power z1 plus z2 is same as e power z1 times e power z2. Simply substitute this formula. That means try to, what is z1 plus z2? You go from right side to left. This is easier. Then, what is differentiation of e power z, which we have seen when we discussed about CR Cauchy-Riemann equations? This is same as e power z. Okay. So therefore, in particular, because this is true, so therefore e power z is an entire function because it is differentiable everywhere, right? Oh, and next one is that uh, we can observe that whatever z it may be, whether z is 0 or z is non-zero, what we have here is e power x is there, which is greater than 0. Okay. So therefore, e power z is always non-zero. E power z is not equal to 0 for any complex number v. Okay. Therefore, because it is a non-zero complex number, we can write this in polar form. Okay. Implies we can write this e power z is equal to some r into e power r, whatever r, either rho, whatever you take, because r we use for z. So you take say rho into e power I phi. Okay. Where this rho is nothing but this uh, e power x. That means argument that length, or if you want, you can write this one. Okay. And this phi is the angle. Okay. That is uh, here whatever you are having is this y or y plus 2n. So you can write here y. So therefore, if you write in the polar form, therefore e power z, you can write this as this row, okay, this e power x, this row into e power iy, okay, or y plus 2n pi. Also you can write, or you can write argument of, right. So this it has exponential form e power I5, okay, for any z where rho and phi are written, right. If you want here this y, you can write as also phi, you can write this y plus 2n, okay, fine. Now the other properties which we can see here is uh, we might have seen all such things are also true in this real case, but are there any properties which are true here but not true here, or some are true here or not true here? We'll see, otherwise there is no point if everything is same, right? So you can check here is that what we know is e power x, e power x is greater than 0 for any real number, okay, but e power z is not that, okay, but e power, if you take I pi, which is cos pi plus I times sin pi, which is nothing but minus. That means what we know, there exist complex numbers okay, such that e power z is a non-negative number, right. Okay, and not only that, you can also observe that e power z is same as e power z plus 2 pi I, because since e power z plus 2 pi I is same as e power z into e power 2 pi I, okay. So but e power 2 pi I is 1, that means this is same as again e power, which shows that e power z is a periodic function, is a periodic function with period 2 pi I, okay, which is not true in this real case, okay, whereas e power x is not a periodic, okay, as e power x is different from e power x plus anything you write x plus, say suppose I'll write here some k where k is any non-zero real number, okay, this is not at all true, right. So these are some of the things. Of course, uh, we'll see properties again and again later. Before going to the other one, we all know e power x, how the graph of e power x look like. Hmm? How the graph of, so we'll see how the graph of e power z is look like. Okay. So for that, we already known is the graph of e power x. It is if I quickly write this, then if suppose this is 1, okay, then it is like, right. Of course it will go very near to x, right. Now if we want to discuss about graph of e power z, which I already discussed earlier, that whenever we want to talk about graph of complex functions, we need to have z and w plane, right. So we should have a two planes. For that, let me draw two planes and we'll discuss. I'll let me take this. This is one, okay. Then let me take another one with another color. Okay. Now, so let me write this as, this is, you can call it as z plane, means z, which is x plus iy, and this is w, which is f of z. Is our function f of z is e power z. Okay, this we will write as w. Okay, our w here is e power z. Right now, simply this 0, you can check here, 0 is mapped to 1 here. Okay, this is mapping to 1. Now, uh, we can see horizontal. For example, you take this imaginary axis. So this is imaginary axis and this is real, right? So if you take imaginary axis, that means imaginary axis, in imaginary axis x is equal to 0. So our z will become simply e power, the z is x plus iy, so this is nothing but I times y. So under this function e power z, what is this will become? So in this case, e power z is same as e power I y, because our x is 0, right? So whatever, that means if you take any point here, if I take any point here, then the corresponding point e power z is e power I y. So where it will be? Where it will be there? We can observe that modulus of e power, that means distance from origin to that point, is modulus of e power z is 1. Okay, so this point w is such a way that the distance from origin to that point w is 1. Okay, so what are all those points? What is a w such that mod w is equal to 1 is nothing but units, right? So this, if you take any point here, or if you take any point here, y, then you will get a let me write this circle. Let's see whether we'll get, even though it is not circle, let me draw on my own. So this, you will get a, you will get a circle, unit circle. So this imaginary axis is transformed to unit circle. Okay, now, what can we talk about? If you will take some line here, a parallel line. Let me try a line. If I draw a line which is parallel to x-axis. Okay, so that means now if I take any line, so if I call it here some x naught, here y naught is fixed and x is varying. So if I take z as x plus I times y naught, then e power z is e power x times e power iy, right? That means again, what are these points? One can understand e power z, if you call it, this is the distance is e power x. Okay, right? Times e power x, and what is, you can call it angle or argument z or whatever theta. This is nothing but y. Okay, right? So those are all points, okay, who's making angle y naught. So how you can draw that here? So let me take this here. Um, this is whatever we are having here. Okay. This angle, what we have here is this y naught. Okay. So if you take any point here, this is say suppose z, then that is mapping to, this is e power z. So this is w, which is equal to e power z. Remember, any point on this line is just like a line starting, remember this 0 won't be there, so I'll make it like this whole. So this 0 won't be there, other than that it starts from that point. Okay, so if you vary, uh, these are all the points. If you want, you can draw it. Okay, so this horizontal line will be mapped to, right. Now you take any vertical line, because we have already seen this imaginary axis is mapped to a circle. Okay, now say suppose take another line. So let me draw that another line. What will take another color? So suppose let me take a line. mm, this suppose let me take a line. Okay, and say suppose this is my 2. Okay, this is x is equal to 2. Okay, that means this is the line where x is equal to this here is 2 and y is varying. Okay, so let me write that. So say x is equal to 2. This line means if you take any point z, so x is 2 plus, so that is same as saying that if you take z, which is 2 plus I times y. Okay, uh, this you here, right. Now sorry, here it is not y naught, is y, because y is, we are varying, y is any point on this line, y is any point. If you take any point here, where it will be mapped to, you can check this. Modulus of e power z is nothing but e square, because this is simply e power z, here is nothing but e square into e power iy, right. So this implies mod e power z is equal to e square. Okay, so all points w are in such a way that from origin to that distance their value is e square, right. So therefore what is this one? It is a circle whose, around circle whose center is origin and radius is 2. Okay, so therefore you will get this one. Okay, my circles are very bad. Okay, so what we have observed is this one is mapped to, right. This similarly, if you take another one, then because the radius is, this length is bigger, you can call it suppose e power some, here it is some k, then the radius will be e power k, right. So that will be like, okay. Similarly, without discussing in detail, you can check that clearly. If you take any line this side, okay, then those lines will be mapped to circles inside this unit circle. Okay, so all lines which are right side to this imaginary axis will be mapped to circles outside this unit circle. So let me write this as unit circle, so that this is our one, this is unit circle. Okay, then all right side will be mapped to outside, circles outside that, and left and left to this imaginary they will be mapped to, right. And in detail you can go that because of periodic function. So if you take this one, this is I pi and this is minus I pi, and you can check that if you have this strip, this this strip, if you write this strip is mapped like, okay. And if you go above here or below this, then again you get same structure like this, circles and so on. So one can visualize this graph using MATLAB or any other things. It's just like circle putting on the other end. Okay, fine. So this is just at least how horizontal lines and vertical lines. The vertical lines are mapping to circles, and horizontal lines are mapping just like lines. Okay, uh, passing through, except that origin it is just like inclined angle that wide. Right. This is about this exponential function. Okay, fine. Now let's back to another one which is again interesting. The second function is logarithmic. Logarithmic. logarithmic function. Okay. Again, how in real case we define logarithmic function? If we call it log x is equal to y, then or if and only if e power y, this should be x. By solving this, you will get this. We already know, right? Or if and only if also you can write. In the same way, how we can solve here is we'll say that we'll solve for the equation e power. We want to find logarithmic function, so we'll consider e power just like say log z we want to find. Okay, so this from here you can observe that log z is equal to w if e power w is z. Okay, so we will solve this equation. So we want to find w, or we want to find solve given z, we want to find solve e power w is equal to z, and that makes sense because we have already seen here what is meant by exponential function. Okay, so how you can calculate exponential function? We want to find w such that e power w is equal to z, right? So how you can do it here? Write w. Okay, so we can write w as say u plus some iv, and z is equal to r. So for that you take z non. Okay, z is equal to r into e power I theta, where theta is the principal argument. That means where our theta is minus between minus pi to pi. Okay. Now if you write this, then e power z is equal to w, you can write as u power u into e power iv, which is equal to z. So therefore it is same as r into e power I theta. And we know when two complex numbers are equal in this form, this is same as saying that e power u is equal to r and v is equal to theta plus 2n, because they are all, it is not just theta, it is plus or minus 2 pi multiple. Okay. This is same as saying that u is equal to, because we want to find what is u and what is v, we are solving for w. Okay, so this u is equal to natural logarithm of r, and v is equal to theta plus 2n. Okay, so if you substitute these two values here, therefore w is equal to natural logarithmic of r plus I times theta plus 2n pi. Okay, where n is any natural number, integer. Okay, so therefore our w is log z, right? So we can define this as for any z non-zero complex number z, we can define log z as natural logarithmic of r plus I times theta plus 2n pi, where n is any integer. Okay, so we can observe that this is a multiple valued function, because for every n you are getting different value, right? So this is the definition of logarithm. It is a multi-valued. Okay. Next class we will discuss about branch current. At that time we will come back to this log function again. Okay, but in this class we will restrict to only what are all different elementary functions, and later in next class we will see about branch, what is meant by branch current. Okay, so whenever we have this log, then and when it is a multiple valued function, we can always have single valued functions, or we can talk about principal value. Okay, so we can also define here what is meant by principal value, or principal value of log z is capital log z, and of course which is, one can easily guess that this is same as I times theta, where theta is a principal argument of given z, minus between minus pi and pi. That means r, we can also say that that is when that n is equal to 0, whatever value we are getting, that is the principal value of log z. We can check that it is a single valued function. Okay. Right? Theta you want to write this, you can write it as capital ER. Okay. So capital log z is natural logarithm of r plus I times capital ER. Okay, ERG of z. Fine. Now, what properties are you can if you want to take some examples for both Ez or um, log z, you find some examples. If you have any difficulty, you can ask me next. So let me write that. One is find z such that e power z is equal to 1 plus I. Okay, that means what you want to write? We want to write this right hand side just like how we have calculated this log z, right? This z you try to write it in r times e power I theta, where theta is the principal value. Okay, so this 1 plus I, obviously you write it into r into e power I theta, then this is e power x into e power y, so find the value of x and find the value of y. Okay, we will get e power z, right? Then second one is also find z such that e power z is equal to minus 2, just like this example. Okay, and e power z is equal to 1 plus root 3i. Okay, and when it comes to log, so find log of minus 1 minus root 3. Okay, this how you will do it here. This is your log z. Okay, so that means your z is minus 1 minus root 3 high. So if you want to find log z, what you require is r, which is 2 in this case, and theta principal value you want to find. Easily can easily check that it is minus 2 pi by 3. Okay, if you plot in that picture, you will understand, right? So then you simply substitute those values here and whatever value you are getting. Okay, if you have any difficulty, you can just ask me next class, or you want to verify with answers, I can give next. Okay. Any other example? Fine. Now we'll see some properties of this log. So some properties. First one, you can observe that this log function is z1 times z2 is same as log z1 plus log z2. Why? This clearly by definition log z1 z2 is natural logarithmic of r, which is nothing but mod z. Okay, here if you want you can write this as mod z also, where r is modulus of z, right? So you here, because I'll just give a hint, log z1 z2 is natural logarithm. Okay, natural logarithm of mod z1 z2. Okay, plus I times you have whatever you have here theta plus 2n pi, right? Where theta is again principal value, or if you want you can write this as argument of z. So instead of writing that, you write this as argument of that, z means z1 times z. Okay, so then you expand using this is same as natural logarithm of mod z1, okay, plus natural logarithm of mod z2, right? Plus I times, we know already argument of z1 z2 is same as argument of z1 plus argument of z2. Then apply, you will get this is same as log z1 plus log z. Okay, but this is again for principal argument, how we have seen is same as this principal of z1 z2 is not equal to log of z1 plus log of z2. So for this you can take just to verify, take z1 is equal to z2 is equal to minus 1, right? Then here also we can notice one thing is that for logarithm, when it comes to real case, we talk about logarithm of positive value. Okay, we don't talk about logarithm of negative value. But here in complex, we can talk about log of any non-zero complex number. So for example, log of minus 1 also makes sense here, right? So how you can calculate this log of minus 1? log of -1. That means you want to find log of natural logarithm of this r, which is 1, right? Plus I times theta, which is principal value. Principal value, because it is -1, where what is this is -1. So angle, this one is exactly whatever you are having angle here, this is theta is equal to pi, right? So this is natural logarithm of r, where r is 1. So natural logarithm of 1 plus I times pi. Okay. So this is natural logarithm of modulus of that is 1. Okay. Modulus of this is 1 plus I times principal argument is pi. So therefore you get this is as I, because log 1 is 0, right? Therefore, but capital log of z1 times z2, which is log 1, this is same as 0, because for 1, what is the angle? Angle is 0. Principal that one is 0. So whereas capital log 1 is 0, which we already expected natural logarithm of 1 is 0, right? Therefore, this log z1 times z2 is not equal to capital log of z1 plus capital log of z2, because this one in this example this is 0, okay, which is not equal to, this is 2 pi I, because I pi plus I pi, which is 2, right? Okay. And this here you can z1 upon z2 also you can check, which is log z1 minus log z2, so that you can, right, you can easily prove this. Log z1 upon z2, this is same as log z1 minus log z2. Okay. These are some of the properties of this logarithmic function and principal logarithmic function. And we can also have some values. For example, if z is a complex number, non-zero complex number, and n, if z is a non-zero complex number, okay, and n is any you say natural number. At present you take natural number, later you can do it for integer also, then what can you say about z power n in terms of this log or exponential? This is same as e power n times log z, okay? And z power 1 by n, if we take, this is again e power 1 by n times log z. Okay, fine. How you can do this? The hint is simple. You can solve it. It is not a problem. Write z as r into e power I theta. Then what you will get is z power n is r power n into e power n I theta. Right? And in this log z, you simplify. You put the value of log z, which is natural logarithm of r, okay, plus I times this theta, okay, or you simply write this as argument of z, okay, argument of z, that if you call it this as theta, and you substitute here e power ni theta, e power n times, so e power n times log z, you can show that this is same as r power n into e power ni, okay. Fine. Either you write this as argument of z or simply call it as theta, because here that theta what we are calling here is one of that argument z, okay. Fine. If you want, you have any confusion, this you can take it as theta. Fine. Now this not no need to restrict with this only n, you can do it for any complex number also. So next elementary function, let me see any examples or exercise I would like to give here. Okay. So we'll go to next one, important one, which is complex exponent. Complex exponent. Okay. So in real case, what we know already is that for if x is any, let me write for real case. If x is any real number and a is again a real number, then x power a, because a greater than 0, we require that. x is greater than 0. So then this is same as e power a log. Okay. So similarly, we can talk about what is meant by. So you take this here. Z is any non-zero complex number. So Z is any non-zero complex number, and you take C is any complex. Okay. Then we can talk about Z power C. Okay. Z power C. How one can define this is same as exponential of C times log Z. Right. Z power C we can define, if you want you can write this as definition. We can define Z power C as e power C times log. Okay. Now you can see here already for n, where n is a natural number, Z power n, we have already this, we can easily verify e power n times log Z, right? But this is true for any complex number, and that is, they are called exponents of this Z. Z power C e power C times log. Okay. One can quickly see one example how we can find this exponents. Example, uh, find the value of okay, so take I power minus anything, you take any complex number, you take a non-zero complex number raised to any other complex number and you find the value. Okay, then let's take some simple one. uh, this I power minus 2i, by definition how this one is e power c, which is this is c, this is just like Z power c, right? So this is nothing but minus 2i into log I. So we want to find what is the value of log I, right? But what is log I is nothing but, you observe here how we have defined log function. This log function is natural logarithm of r. So here r is modulus of that z. So here z is I. So natural logarithm of z, which is mod I, which is 1. So here you will get natural logarithm of 1 plus I times I times that theta plus 2n pi, where theta is a principal value of that z plus 2n pi. So here our z is I. Okay. So therefore the principal value is pi by 2 plus 2n, right? So because our this is I, so therefore what is the angle? This angle is pi. That is principal, right? But we know this natural logarithm of 1 is 0. So this is simply I, if I take pi I common, and then 2 also if I take, then this is 1 plus 4, right? So therefore if you substitute those values, therefore I power response little late. Okay. So therefore I power minus 2i is nothing but e exponential of minus 2i into pi I by 2 into 1 plus 4n. Of course here n is a any integer. Okay. N is any, right? So therefore this is nothing but I and I square, which is minus 1, 2 will get cancelled. So e power pi into 1 plus 4, which is for any n. You can check that this is a real value, right? Real value. So this I power minus 2i, okay, this takes infinitely many values, but they are real value, right? Okay. Again, this is a multiple valued function. So whenever we have a multiple valued function, we can talk about principal value, right? So you can define here um, principal value of the exponent z over c, okay, is defined as, you can simply call it PV of zc. This we can define as, obviously what is there, because here log z is multiple valued, so therefore that log z, we have principal value which is capital log, right? So whatever value we are get, that we define as the principal value of z. Okay. So just take an exercise. Find principal value of minus I whole power and see what you will get. Okay, that means here you should get single value. Okay, fine. Of course, you can also find the value of direct value of minus 5 whole power I, which is a multiple value. Okay. These are all about, and now whatever you see in our real, like trigonometric functions. Okay. What are all we know in trigonometric functions in calculus? Is say suppose we have here is just like sine h. Okay, so sine x and cos x in terms of e power x and e power minus x. So similarly, you will have sine z. Okay, so just what is this one? E power iz minus e power minus iz upon 2i. Okay, and what is cos z is e power iz plus e power minus iz upon 2. And if you for I less, what we have is e power ix. So similarly, you can have e power iz, which is cos z plus I times sin z. Of course, from this also you will get easily this, and so many other like sine hyperbolic sine hz, okay, which is e power z minus e power minus z by 2. Similarly, cos z e power z plus e power minus z by 2. All other things, whatever we have in real, it is same. Okay, and I don't need to discuss. Whoever want to know more formulas, you can refer the textbook. So refer textbook for more formula whatever we have and their proper. Okay, formula. What is little different that at least we can see here is inverse trigonometric function. Inverse, and one at least we can discuss this sine or cos whatever. For example, we want to know what is sine inverse of z. How can find the sine inverse of z? Okay, how we will solve sine inverse of z? Number w. Okay, when this will be true, obviously just like in real case, sine w should be same as z. So we'll solve this and find the value of w, right? And we have at least written here what is sine w is e power iw minus e power minus iw by 1, right? That means e power iw minus e power by 2i is equal to z, right? This is same as if you simplify this is e power iw, right, minus 1 by e power iw by z, and if you write this as quadratic 1 minus 1. Okay, that means, and you bring it here, this means 2iz e power iw minus 1 is equal to 0. Okay, now if you consider this as a quadratic equation in e power iw, which is a complex number, then what roots we get here is e power iw is equal to minus b, which is 2iz, okay, plus, or you no need to write plus or minus, this is same as square root of b square, okay, which is this much is b square, so 4 z square I square, so it is minus 4 z square, right, and minus 4ac, so this here what you will get is plus 4, right, and then whole power 1. See, I can write here minus, but because this is z power 1 by 2 is there, okay, so therefore this is same as just like a multi-valued function, right? 1. So these are the values, or if you want you can put it minus here, it is not a problem, because 1 minus z square whole power 1 by 2 is valued. Okay, that one should remember. Or if you have any difficulty, you can write minus also, it is not a, just like in how we write in real quadratic. In real, you usually have a single valued function, so that's why we write plus or minus here. Otherwise, we in complex you don't require, anyhow it takes two values. Okay, that's don't want to here is So if you simplify this, what you will get here is 2 will get cancelled. I z minus this is 1 minus z square whole power 1 by 2. Okay, plus this you can write here plus y minus z. Okay. And of course, remember every time this is it taking two values, one and the other one is minus, right? So this is the e power iw, right? Hence, what is iw? This implies iw is log of this iz plus 1 minus z square whole power 1 by 2. Then by multiplying by minus I, what we will get is w, which is minus I of iz plus 1 minus z square whole power 1 by 2. So therefore, our w is sine. Okay, we are solving for w, which is sine inverse z. Therefore, sine inverse z is minus log iz plus 1 minus z square whole power 1 by 2. Remember, this is a this 1 minus z square whole power 1 by 2 takes two values. And here you have log, which is again a multi-valued function. So therefore, this is multiple value. Sine z is a multiple valued function. Okay. It is not difficult. You can take any z, which is a complex number, and try to find the values of sine inverse z. Similarly, you can find the value of cos inverse z. So if you want to take it as exercise, find, or I will also give the answer so that you can just find whether whatever you got is correct or not. Okay. So show that cos inverse z, like how you simply simplify that. Instead of here whatever we have e power iw minus e power minus iw by 2i, what you will get here is e power iw minus e power plus e power minus iw by 2. That you simplify, okay, and show that this cos inverse z is minus I times log z plus I into 1 minus z square whole power 1. Okay, fine. And take one more, solve z cos z is equal to root. That means it is z is nothing but cos inverse of root, right? That means you want to find what is cos inverse of root 2, right? Is that clear? Fine. So these are all about elementary functions. In next class, we'll discuss about these things will come again and again. Okay, in further classes, all these elementary functions will be coming again and again. So in next class, we'll see what branch cut, branch points, those things, and with examples. That means whenever we have a multiple valued function, then how we can get single valued functions so that we can talk about their analyticity, all those. So that is concept of here branch cuts and branch points. Okay, that we'll see in next class. We'll stop.